Module 6, Polar Coordinates and Applications. Specifically, Lesson 18, Polar Coordinates and Equations. In this lesson, we are going to be talking about polar coordinates, which is another way of referencing where an object or individual is in reference to your position. This is going to be in contrast to the rectangular or the Cartesian coordinate system that uses values of x and y to demonstrate how far an object or individual is horizontally and vertically. Polar coordinates is going to work a little bit differently. With an origin point, known as a pole, and a ray, known as a polar axis, a point P is located using two coordinates, r and theta. In the polar coordinate systems, r represents a directed distance from the pole, and theta is a measure of standard rotation from the polar axis. You may interpret either the value of r first or the value of theta first when graphing a given point r, theta. So what we already have here is a difference based on how the Cartesian system works. The Cartesian or rectangular system essentially asks you to move some amount horizontally and then some amount vertically, or move some amount vertically and then some amount horizontally to get to your final position. The way that polar coordinates works is that you are going to have an angle measure and a distance, meaning that all we need to do to point out where something is to say how far do we need to turn to face that object, and then how far do we need to walk to get to that object. Or walk forward some amount and then rotate in order to land upon your object. Some people tend to compare polar coordinates to tank controls, where you stop at one point where your pole is, that is your position, and then you turn before you move forward or backwards. Now, even more different with polar coordinates compared to Cartesian is that unlike a point xy in Cartesian or rectangular coordinate systems, a given point r, theta in the polar coordinate system does not have a unique representation, and instead has infinitely many representations. Now, what this means and why is that when I have one point represented, for example, the point on this graph up here, r, theta, well, I can also end up at that same point with a different angle measure. For example, if I still want to have that same directed distance of r, but instead of theta, I add another full rotation to this. Well, if I add another full rotation or add 2 pi radians to it, then I'm still going to end up at the exact same point. Meaning, I could represent something like, let's say 2 pi over 4. I could represent this polar coordinate also as 2 pi over 4 plus 2 pi. These 2 points are essentially the same because they end up at the same place. So I can represent that point using already 2 different ways. And I could add maybe more instances of 2 pi. So add maybe 4 pi to this. This would still end up at the same place because it has the same terminal edge. Or instead, maybe I wanted to subtract 2 pi. That would also work. You will also see that when we consider negative radii, we can also represent points in other ways. A negative radius in polar coordinates means that when you have rotated a certain amount based on theta, r means face a certain direction, and negative r would mean walk backwards from the direction that you were facing. Negative is just a direction of movement. So, for example, if I wanted to end up at the same place as 2 comma pi over 4, what I could do is consider instead having a negative radius, so walking backwards 2. But if I want to walk backwards 2 and end up at the same place, in this case 2 comma pi over 4 would put me in quadrant 1 of the standard unit circle. If I want to end up at the same place, then I'm going to need to face in a different direction or have a different angle measure. Instead of pi over 4, if I instead, for example, add pi to that, which would give me 5 pi over 4, that would mean rotate to 5 pi over 4, which is in quadrant 3, and then when facing your angle measure in quadrant 3, walk backwards a distance of 2. That would put me, therefore, in quadrant 1. That's why we can have many different representations for the same point, which has a lot of implications with how the polar coordinate system works compared to a rectangular coordinate system. One final note I'll make about this real quick is that the picture that I have up here for the polar coordinate system, note that technically the only things that are actually part of the coordinate plane for polar coordinates is just the pole and the polar axis. So realistically, you just have a pole and a polar axis. We tend to just draw these traced circles for convenience, as well as these vertical and horizontal lines that look kind of like the x and y coordinates or the x and y axes. We just draw those for convenience as well for reference to a currently more familiar coordinate system. But they are technically not part of the actual polar coordinate system itself. The only things you need for a polar coordinate system is a pole and a polar axis.